Yeah. Okay. And one has to be admitted. So, okay, I guess they got admitted. Yeah. Maybe if I do full screen, somehow I lose this control. Anyone knows how to make this waiting room go away? No, okay. So next time I'll be careful. So, okay. Maybe I'll just see one more time. Okay, let's not worry about it. I don't think there is a way to do it very easily, at least. Okay, so let's start. So as I was saying, we will review. So, so for a ring with unity, an ideal is a subset which satisfies these two properties, that is closed under addition and is closed under multiplication by an element of R and an element of I. And if the ring is not commutative, then we have a notion of left ideal, right ideal, and two-sided ideal. And all these three notions agree when the ring is commutative. So as I said, we'll study mostly commutative ring. So occasionally we'll refer to non-commutative rings, but our center of attention will be commutative rings. So our subring is a subset which is closed under A minus B and A times B. Yeah, so this is A minus B is a funny way of making sure both addition and inverses are in there. Yeah, so some standard trick which you must have learned in group theory.
Excuse me, sir.
Yeah.
Sir, I think there is a method to.
There is a what?
Sir, are you using a laptop or a PC for that? Okay, so sir, in the Zoom screen, there is a participants tab at the bottom, right? The chat, share screen, record, participants.
Yeah.
Beside the participants, there is an arrow.
Beside the participants, okay, here. There is no arrow in my thing.
Oh, there should be one. There is one in mine, but I don't have this feature.
I have.
So it's only with the host.
I can.
But
I can click on participants. Maybe if I pause sharing, then it will come up. Let me just stop sharing and see if it comes up. No, I have 44 participants, but
there's no arrow beside it.
There is no arrow beside it, unfortunately.
Okay, should be one. I'm not sure why it's not coming, but there should be one.
Yeah, maybe.
Sir, if you could just make someone of us the host, we can try it once.
Yeah. How do I make someone a host? Maybe.
You click on the person's name and then make.
What is your name? I'll make you the host.
My name is Snehan, sir. Snehan Sen.
Snehan Sen. Spell your name again.
Snehinh Sen.
Sneha. Snehan. No, I can't.
It's a Snehan Sen. That's me.
Yeah, say your name again.
Snehin.
Yeah, I found it. Yeah.
So then you can continue the class, and I'll try my best to stop.
Make host. Okay, good. Yeah. Unfortunately, everything is being recorded. It's okay. It's just us who are seeing it. I have put it in YouTube, but it's restricted viewing. Okay.
Yes, I have disabled it.
Oh, you have disabled sharing, screen sharing for me.
Oh, sir, then I'm making you the host. I have disabled the room. So now it won't be a problem.
Oh, I see. But I can't share the screen now.
Sir, I'm making you the host. So
okay.
Now you can.
Okay. You have disabled the waiting room. Okay, great. Okay. Yeah. Okay. Okay, great. Yeah. So, okay. It's being recorded, I suppose. So no issues with that. Yeah. So yeah. So now you can see this z square root 2 is a subring of R. So it's there are two ways of thinking about it. One is the smallest. So you can consider all subrings of R which contains z and square root 2 and take their intersection. So that will be a subring of R. That will be also a subring of R. And another way is to consider this set. So these two agree. Yeah. So maybe I'll just write down the statement we'll have to prove. Yeah. So maybe I'll just put it here. So intersection of subrings of a ring is a subring. Yeah, so it's, I mean, it's not deep. It's like intersection of subgroups is a group. So it's about the same level. Then we will, so this statement, I'm not showing that these two sets are same, but as something similar also, and then the proof is, proof for this would be same. So this is one interesting subring of R. So maybe one wants a subring of Q which is different from Z, then what you can do is take a subring which contains both Z and half. Yeah? So the smallest subring of Q containing Z and half. So so what is the what can you how do you describe such a subring? If I want to give some explicit description like this, what will be the description? So we know half will be there. So of course, half plus half is 1. 3 over 2 will be there and so on.
Z plus half for Z integer.
As yeah, like binary expansion with finitely many ones.
Half.
A binary expansion with finitely many ones. So in decimal, yeah, that is what you are trying to say. Yeah, so that is one way of thinking. But I wanted as a subset of Q. Yeah, so what fractions are allowed? So see how the half
Those
is
with
allowed.
Reciprocal power of 2.
Yeah, so all powers of 2 are allowed in the denominator. Yeah. So what you can say is
P half where P is a polynomial with rational coefficient.
So polynomial description is not as compact, so we'll come to it. But this is a very compact way of writing it. Yeah. So so this is what it is. Z half is precisely a over 2 power n. N is some integer greater equal. I can make it 0. Yeah, greater equal 0. N in Z. N. Yeah. So this is a so of course you can check that these guys are in there. Yeah. Both the directions are okay. So first thing you can check is that Z is of course in the set R. So R is defined to be this guy. So of course you can see Z is in there and half is in there. And this is a, so one has to check that this is a ring as well. Yeah. But we will check that. In fact, checking instead of checking this, what I'll show is that R is contained in this, and this we already know is a ring. if we assume that intersection of subrings is a subring. Yeah. So as I said, R contains Z half is clear. Now let's take alpha in R. So so now I want to say that R is contained in Z half. Yeah. So alpha is of the form A over 2 power n for some A and for some n greater equals 0. Then alpha you can write it as A times 1 over half power n. I mean, this is a sort of obvious. I mean, the proof is not deep, is what I'm trying to say. Yeah. But A is an integer, so and this is the subring, smallest subring containing Z and half. So it so this whatever this subring is, Z half, it contains A and it contains half. Yeah, so it contains half power n as well. You multiply half to itself n times. That will also be contained in Z half, and A will also be and A is an integer, so that is in Z half. So their product is also in Z half. Yeah. So what we showed is that alpha, taking any arbitrary alpha in R, it belongs to Z half as well. So that tells you that R is contained in Z half. So those two show that these two sets are same, and this guy is a ring, so the other side is also a ring, is a subring. Yeah. So that, I mean. So these two are subrings of R. This, in fact, the second one is a subring of Q. But we will see later on when we do some modules and etc. We'll see that they are very different subrings in some sense. Yeah. So somehow they are very different. I mean, so in particular, they are not isomorphic. They are not going to be isomorphic. Yeah. This Z square root 2 and Z half are not isomorphic subrings. Then another subring which is entirely different from the other two is Z pi. Yeah. So this is so how does the element of Z pi look like? So I want to convince you that Z pi is precisely this thing. Z pi means this, again, the definition is the smallest string containing Z and pi. Yeah. So if there is a ring which contains Z and pi, it will contain these polynomials, these expressions, these numbers, yeah, because all these operations are ring operations. So it contains A0 and it contains A1 and pi, so it contains A1 times pi, and so it will contain A0 plus A1 times pi, and so on. Yeah, so this is how you can argue that the right hand side is going to be contained in the left hand side, and of course the left hand side is contained in right hand side is trivial. Yeah, so this equality holds. So of course even Z half you could have argued this way, and that it's this, but that doesn't come out to be as compact an answer as this one. Yeah, so you can simplify and see that if you write it this way, it comes out to be that expression at the end if you combine things. Yeah. So, this is something similar to what is called polynomial rings. So we will come to the definition of polynomial ring in a bit. But let's try to look at this example Z half in somewhat. So instead of Z half, I'll change the example a little bit. Zi. Yeah. So Zi is also is a subring of complex numbers like Z square root 2. That was a subring of R, but R is a subring of C, so it's also a subring of complex numbers. So both of them are subrings of C. Yeah, and the question is, so it's not so it's sort of intuitively clear that Z pi and Z half and Z square root 2 are very distinct subrings, meaning they are non-isomorphic. But what about Zi and Z square root 2? Are they isomorphic?
No, sir.
Yeah, so they are no. Why is that?
Because I is getting mapped. If I is mapped to say alpha, then alpha power 4 should be the identity. And
Yeah.
I also know that 1 and -1 and -I are also there. So there are 4 distinct elements which are being mapped to 4 distinct elements which are real and all of their fourth power is identity, but that's not possible. There are only 2 possible answers.
Yeah, so basically you have to see, I mean, if they're isomorphic, you have to see where I can go or where square root 2 can go. Yeah. So I mean, it has nothing to do with even if I had put square root 3, it won't be it will be a problem. They won't be isomorphic. So square root 2 has to go to some element. So maybe I'll give you a proof. So if you have a yeah, unfortunately, so maybe this is not a bad place to recall what homomorphism are. So maybe if first just recall a map phi from these two rings between these two rings is said to be a ring homomorphism. So I've changed the operation so that it becomes clear. Yeah. So this is how you must have learned in group theory initially, I hope. And so one should be careful, which, I mean, later on all these operations are assumed to be have the same notation, but from context we understand what where the operation is happening. Yeah? So suppose phi is a ring homomorphism, so maybe I'll just do it here. So phi is, say, a ring homomorphism from Z square root 2 to Z square root I, yeah, or Z square root 3, whatever you like. Yeah, then where can phi square root 2 go? Yeah, what should be phi square root 2? So if you think so this is contained in C. Yeah, so where would phi square root 2 go? There are not too many options for it. Yeah, so note that phi of square root 2 times phi of square root 2, what should that be? That should be same as phi of 2, right? And well, phi of 2 is same as phi of 1 plus phi of 1. Yeah, so this is 2 times phi of 1. And where will 1 go? 1 has to go to 1 under this ring homomorphism. Yeah. So that tells you that this has to be equal to 2. So that tells you that phi of square root 2 has to be a number whose square is 2. And there are only 2 possibilities. One is square root 2 and the other is minus square root 2. Yeah, among complex numbers. So that tells you that, so this implies phi of square root 2 is square root 2 or minus square root 2. Yeah. And neither of those two are in Zi. Yeah. So one can argue similarly with Z square root 3, or you can start with Zi. And so what the other argument was, so the I happens to be a unit in Zi, and minus I is also a unit in Zi, and 1 and minus 1 of course are units in Zi. So there are 4 units in Zi, and in Z square root 2, so one has to see how many units are there. Yeah, so there are more units in Z square root 2 as well. So yeah, so just by counting units, one may not be able to get, but basically same argument. Where will I go? I has to go to something whose square is minus 1. But this is contained in real, and in real number, none of the real numbers have square in mind, has square minus 1. Yeah. So that tells you that you can't get a ring homomorphism from Z or square bracket I to Z square. Yeah, makes sense? Okay. So let's make this check this observation. Intersection of subrings of a ring is a subring. So maybe I'll do it with black pen. So proof. So I mean, since this is the first course in ring theory, I should prove these statements as well. So let R be a ring, and this collection R alpha. So we have a collection of subrings, yeah, which we will denote by R alpha, some indexing set alpha in maybe I looks more like an ideal. So let me just change this to omega. Yeah. Alpha in omega be a collection of subrings of R. Yeah, so omega is some indexing set. Omega, an indexing set. Yeah, then what we want to show is that intersection of R alpha is a subring as well. Yeah, so let R naught equals intersection R alpha in omega, then R naught is a subring. So of course R alpha plus is well grouped, so R naught is an additive subgroup. So I'll just appeal to the group theory, additive subgroup of R. Basically, if you take two elements A and B in R naught, then these A, B's are contained in R alpha for each alpha. So A minus B is contained in R alpha it belongs to R alpha for each alpha, and hence in the intersection. Yeah, and similarly, same argument holds for products. So A, B belongs to R naught implies A, B belongs to R alpha for all alpha in omega implies A dot B belongs to R alpha for all alpha in omega, and then this last statement implies that A dot B belongs to R naught, the intersection of all these guys. So not the first one, but the second one. So okay, so we sort of started a bit late, thanks to Zoom Baba. So maybe you want a break, or should I continue? Maybe we'll take a break after we complete this polynomial ring definition. Yeah. Okay. This polynomial ring is mostly, we sort of know philosophically what polynomial ring is. So Z pi is sort of like a polynomial ring, yeah, but we think of it as a subring of R. So we'll make this a little formal, yeah. So let R plus dot be a commutative ring with unity. So commutative is again not necessary. Ring with unity is enough, yeah. So you can define a polynomial ring even over a non-commutative ring. But if it helps you, you just think of it as a commutative ring. The polynomial ring Rx over R. So this is so I'm not really giving a definition here. It's more like a, so if I write a definition like this, the polynomial ring Rx over R consists of polynomials with coefficients in R with polynomial addition and polynomial multiplication as binary operators. Now, of course, there is some problem with the definitions. One would ask what polynomials are and what is polynomial addition and polynomial multiplication. So we will give a more accurate, more formal definitions in a bit. But you think of them as a set consisting of polynomials in the way you think of polynomials. Yeah? Polynomials with real coefficients or with rational coefficients. So you think of them as some God-given thing in some sense, right? Like integers or real integers, and then you cook up rational numbers and so on. But you sort of think of them something concrete. Yeah? So that is how we think of them. And we know what the polynomial addition is, right? So to add two polynomials, we just add in the usual polynomial addition way. And we also know what polynomial multiplication is. So, but when we want to define it in abstract mathematics, where the rings are sort of funny looking, I mean, it need not be a subring of a complex number, let's say, could be some abstract ring, yeah. And then one should do things more concretely, so that there is no, so that when someone has to check the proof, one can go to these formal definition and verify everything is fine. But when we think of it while proving, we don't think of it in that weird way. Yeah. So what is a polynomial ring? So one way to think of it formally is that you think of it as functions from non-negative integers to the ring R. Yeah. Such that all but finitely many are at all but finitely many these functions is 0. So in other words, they exist n such that ei is 0 for all I greater equal n or greater than n. It doesn't matter. Yeah. So, but let me just put strictly greater than here rather than so greater equal. I mean, the other definition is not wrong, but let's just do this. Okay. So this as a set we know, because we know what z greater equal 0 is. R is given to us as a ring, and we know how to we know what a function is. Yeah. So I guess when you were doing in first year, you must have learned what a formally also what a function is. So this set is now clear to us, crystal clear to us. Now we should define what a polynomial, what addition and multiplication on this ring is. So to define addition, so I've put this. So R has this plus and dot. So I just to make life more complicated or more crystal clear, depends upon how you want to think about it. We'll change the operation for Rx. Yeah. So this A. So if you have two elements A and B in, yeah, maybe I should put this for AB in Rx, the polynomial ring Rx. Yeah. We define A plus B. We have to define it as a. We have to define a function from Z from non-negative integers to R, and the definition is precisely this. Yeah, and A dot B is defined this way. Yeah. So of course I should. Yeah. So maybe I should. I thought I wrote that somewhere. Yeah. So I have it here. Yeah. So given A, you think of the traditional way of making a function into a polynomial. Traditional way of thinking of this function as a polynomial is this. Yeah. So you think of it as an x power n plus an minus 1 x power n minus 1 dot 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 a0, where n is the maximum of these guys. Yeah. Where for which ai is non-zero. Okay, so then of course addition. Then this is how you add two polynomials, yeah, and this is how you would multiply two polynomials. So I'll come to it in a bit when, but you just take it. So this is how we. So if you want to find the degree of the coefficient of x power n, let's say, then this is how we find the coefficients of x power n in the two polynomials in the product of two polynomial a and b. Yeah. we take the ith coefficient of x power I of A and coefficient of x power n minus I in B, where I is some number less than n, and we add them together. So that is what this funny multiplication looks like. So this is not, so this looks a bit weird, but I mean, if you think in terms of polynomial, this is not at all weird. Yeah.
So we are always treating x as a formal variable, right?
Yeah, so right now x is not there, it's more of a notation, yeah? So if you're looking at the formal definition, there is no x. Yeah, it consists of functions and these are the operations. But we don't think of polynomial as functions, yeah? We think of them as these expressions. So once the formal thing is done, then we will always think of polynomial as this expression. This is just to make the foundation accurate, yeah? So there is no confusion about what it is as a set and so on.
Okay, thank you.
Does that make sense? Yeah, okay, good. Yeah, so there is, at the moment, in the formal definition, there is no x. It's just functions and stuff, yeah? So the first statement is that Rx is a ring with unity, and if you assume R is commutative, then Rx is also a commutative ring with unity. Okay, so this I already said. Yeah, so this n is called the degree of A, which of course, again, we know that this is what the degree of the polynomial is called. Yeah. So let's see. Yeah, so maybe this is a good time to take a break. So maybe we'll do a 5-minute break, and then we will start. Yeah, with the proof of this proposition. Okay. So I'm here. So if you have some questions, you can ask me. But if you want to see away from the screen, just go ahead and see something far away. Yeah, so let's assume. Yeah, so we want to start we want to look at the proof of this thing. So yeah, so I don't know. Okay. I can make this bigger. Yeah, so I guess the definition is in there, yeah. So we want to check that this is a ring. So I'm not gonna do all these steps, but we will see some of these steps, yeah. So we basically will have to check all the axioms. So first thing is one has to check is that it's an abelian group. So that means given an element, one has to So it's already, I mean, this is a binary operator. We have to show that it contains the identity and it contains the inverse. So I guess I forgot to write down what this. So the zero function, yeah, the zero function is the identity element. So maybe the zero function. That means the function which sends any integer, any non-negative integer to the zero element of R. So zero of I is equal to 0 of R. Somehow this writes very thin. Okay, let's try this. This is better. The zero function is the zero element of the ring. So it's the additive identity. And then every element has a negative, so it has an additive inverse. So if you are given a function element of Rx, that means you are given a function, yeah, a from non-negative integers to R. So I have to define a function which from non-negative integers to R with this property such that is the additive inverse. So that function is B. I'm declaring Bn to be minus An for all n in non-negative integers. And what happens then? This of course belongs to Rx because after some point A takes value 0. So at that point onwards, even B will take value 0. So it does belong to Rx. And if you compute A plus B, by definition, A plus B is a function whose value is 0 at all non-negative integers. Yeah. So you get the zero function. And check. So maybe here, check zero function is the additive identity. Additive identity. So this is I guess this should have been the first step to check that the zero function is additive identity, but again that is quite obvious, right? So if you add the zero function, you don't change the function. And then this plus is associative. So that pretty much follows from the fact that the plus in R is associative, because that's how it's defined. This is basically component-wise addition. Yeah. So if you remember, we talked about functions from 0-1 interval to R, and continuous function. So there I said, I mean, continuity is sort of fake. Even without continuity, you get what you get is a ring. Yeah. So in fact, if you are given any function to if you are given any set x and any set u and a function, and then you can consider set of all functions from u to real numbers or u to any ring, that will also be a ring. So here it's set of so here the underlying set is non-negative integers, and the target is not real number but some ring, but it doesn't matter. Okay. So this is associative. Similarly, this dot is associative. So these two are routine. So no, dot is associative is not routine. So let me meaning it is routine, but it doesn't follow from component wise. So this is something which one has to verify. Yeah. So maybe I'll do this point below. Yeah, so let's try to do dot is associative. Yeah. So this is same as saying the polynomial multiplication is associative. Yeah. So okay. So I don't know. It's going to be a bit messy because we know this. Okay. So let's say A. BC, but let's do this once. Be 3 elements in Rx, yeah. Then A dot B dot C, yeah. This is our guy, and we want to evaluate it at some number n. Yeah. So what is this function evaluated at n? We want to show that that is same as A dot B dot C evaluated at n. So let's try to do this. So by definition, this is same as summation I equals 0 to n A dot B of I evaluated at I times C of this sorry, so this I've got the notation a bit clumsy, so let me just fix that. So this is the multiplication in the polynomial ring, and this dot is a multiplication in the usual ring R. Yeah, C n minus I. Yeah. So this is the value of this function at n. So this hasn't been expanded yet, so I have to expand. So it will turn out to be a double summation. So equals 0 to n, and let me just expand this part as well. So this is A dot B of I is maybe j equals 0 to I, A j, and times B. So this is the usual ring multiplication, R multiplication in R, not Rx. B I minus j times C n minus I. Yeah, so this is how it comes out. And if I do then the other way, so A dot B dot C evaluated at some n. Yeah, and then if I show that this happens to be same as this guy, then the two functions are same because they take the same values for all n. So n is some natural number. N is some number greater or equal 0. Yeah. Some non-negative integer. So what is this? So this by same method is a. Let me write it in a funny way now. So j equals 0 to n aj b dot c of n minus yeah. So I don't know if this is a good idea. No, let's write it I itself. Yeah. So I think we'll have to change the order of, but it doesn't matter. But I think it will come out. So I don't think this will be complicated. So it shouldn't be complicated. Yeah. N minus I. I equals 0 to n. And are you guys with me? Hello?
Yes, sir.
Yes. Okay. Okay.
Yes,
Good. Okay. Yeah. So I equals 0 to n ai b dot c n minus I, and then of course you expand this part as well. So this is I equals 0 to n, and summation j equals yeah. So 0 to n minus I. So everything is sort of changed. AI. So this is the ring product. Yeah. AI dot b j and dot c. So here there should be a dot c n minus I minus j. Yeah. So this is what the definition says. Yeah. Okay. So now, yeah, so some change of variable will give you this thing. So what is that change of variable? That these two sums are same. Yeah. So let's see. Yeah, so maybe you take k to be n minus I, okay. Then the second sum becomes, yeah, so then I want to write everything. So n, I want to get rid of I, yeah. So that tells you that I is, maybe one has to change the order of summation. Yeah, so let's try to change the order of summation and maybe one will get it. Yeah. So let's see.
So if you consider I and I plus j, maybe it could be something.
Yeah. Yeah, so let's try to write the summation in a, so this is same as summing over, yeah, so this is same as summing over I and j. So they are greater equal, they are less than equal to n. Okay, at least the first one. Maybe this is what, okay, so this is n minus I. Yeah, so I really want to change the order summation. This looks, this doesn't look good. So, so what is, so let me just try to reinterpret this sum, yeah. So I will vary from 0 to n, j will vary from 0 to n minus I, yeah. So 0 to n minus I. So j is less than, yeah, so this is I and j is less than I and j is actually less than n minus I. Okay. Yeah, so one has to change some variable. It's not just changing the order of summation. Yeah, so let's change the variable. Yeah. So it's not, I mean, one has done this in polynomials. It's written in function form, so it looks a little more scary. But it's just checking that multiplication is associative in polynomials. Yeah. So so just put.
Sir, in the first expression, you can write j equal to 0 to n and put an indicator j lesser than equal to I, and then change the order of summation.
So that will resolve the problem.
Yes, because then both the upper bounds will be the same. So I mean the inner expression won't, the inner limits won't depend on the outer one. So you can change the order of summation then.
Okay. Okay, so maybe it can be done that way. Yeah. So, but let me just try this. Uh, n minus I. I'll try to do set k equals n minus I, and then I becomes um, n minus k. Yeah. And let's try to see if I get that expression. So set k equals n minus I, and then this expression becomes I equals k equals n minus I, then yeah, so if k goes from 0 to n, sorry, I goes from 0 to n, then k will also go from 0 to n, that is okay. So k goes from 0 to n, yeah, because k is n minus I, yeah. So when I is 0, k is n. So but it goes in the reverse order, but it goes from 0 to n, so that's not a problem. And j is goes from 0 to k, yeah, it goes from 0 to n minus I, yeah, which is same as k. Okay, yeah, so this looks okay, and this becomes ai is a, so I don't know, I is n minus k. Okay, it doesn't help, looks like. And b bj and c n minus I is k, so k minus j. So it didn't help. Okay.
So,
Yeah.
excuse me, sir. So we can try putting I plus j equals to k.
I plus j equals k, that will, yeah, that seems, yeah, that will make this n minus, yeah, so maybe that is a good suggestion. So let me try to do that, yeah. So it's okay, we are going a little slow, but this is how things happen in classroom, yeah. So k, set k equals I plus j. And then maybe it's okay, yeah. So k equals, okay, so if I do k equals I plus j, then I have to replace one of the variables, yeah. So which one should I replace? Maybe I'll keep I and I'll get rid of j, yeah. So j equals, so this implies j equals k minus I. So wherever there is j, I'll replace it by k minus I. Yeah, so this summation becomes I equals 0 to n, and j varies from 0 to n minus I, but so if I want to write it in terms of k, then for k, j to vary from for j to be 0, k must be I, yeah, and for j to be n minus I, k must be n. So k varies from I to n, yeah, and this becomes, so what's inside becomes ai b of j is k minus I, and c of n minus k. Yeah, so this is what we get. Does it look somewhat similar to this guy? Somewhat similar, but yeah, k varies from, so k is bigger, so there's a slight difference. Hopefully, now one can change the order of summation, then it will come out okay. Yeah, so
You can consider like n minus k, and then something.
say that again.
We can consider over here, instead of k from I to n, we can consider n minus k, some L equal to n minus k.
Yeah,
Or
so
something.
yeah, so one can think of it, this is sum from I, k, so k, there are two variables basically, greater equals 0, I is less than k, less than n, yeah, and summation over I and k with these guys in there, b k minus I, and Cn minus k. And the other sum is also same. Yeah, so it's essentially the same, but maybe, so now this guy, let me just write that down. So that is sum over I, but now this j is less than I. Yeah, so j is less than I, less equal I, less equal n, and greater equal 0. So again, it's just that you have to replace I by j and k by I. Yeah, and you get aj, b I minus j, and c n minus I. Yeah, so if you make this change, I goes to j and k goes to I, k goes to I, then you get this expression in this one. Yeah, so these two are same. Okay, so I suppose this is convincing enough that that this is associative. Yeah, so this is dot is associative. So once everyone should do it. So I volunteered for you guys. So this is associative. I don't want to try now distributive laws, but it's like in the polynomials, as I said. So you know that distributive law works for polynomials, and the sum and the product is defined exactly like polynomials. So the distributive law works. The identity element, the unity of the polynomial ring is this function 1 Rx. What it does is it sends 0 to 1 and the rest of them to 0. Yeah, so this is how you will define a constant, right? The 0th, the function should take the 0 to that constant, and all the higher degree coefficients must be 0. Yeah. So, so the value of the function at n is the coefficient of x power n. That is the convention we have here. Yeah. So this is so it's easy to check that this is the multiplicative unity. So maybe this also I can check because I think this is easy. Yeah, or let me just leave it for you. Yeah, so you just do this multiplication. You'll see that I mean everything goes away except because most of them are 0, right? So what you get is just a, so a dot 1 of n is just an. Yeah, so that is all you'll get because the rest of the terms are 0. So just from this expression, if you plug in, you pretend b is this 1 sub Rx, then you can see that you get a dot b of n is just an, because the other terms, because b is going to be 0 whenever I is different from n. Yeah, in this expression, in this expression. Yeah. Okay, so so this is a this is the unit, the multiplicative identity, and then when R is commutative, then of course the multiplication, whether you multiply AI dot Bn minus I you do, or Bn minus I dot AI, it doesn't make any difference. Yeah, so that's why Rx is going to be commutative. So these are some easy observation just by looking at this formula. Yeah. So what you get is that when R is a commutative ring, then Rx is a commutative ring. So and one more thing is that there is a ring homomorphism from R to Rx, yeah, which basically sends any element to the constant term. Yeah. So the map R to Rx, which sends A to Fa, where Fa is that function. Maybe I should have called it Ca for constant. Yeah, but never mind. So in this map, what does it do? It sends A to this map, which I called it I. It's some natural map. Yeah, so we will think of R as a sub. Yeah, so this is an injective ring homomorphism. So let's see why this is a injective ring homomorphism. So of course, I is an injective function is clear. function is clear, yeah, because I mean if A, since you can recover A from FA, yeah, since A FA equals, since FA equals FB implies FA 0 equals FB0, but by definition FA0 is A and FB0 is B. Yeah, so that tells you that A equals B. So I is an injective function. So remember, what does I do? It sends A to FA, where FA is the function which is the constant, is the function which takes 0 to A and every other n to 0. Yeah, so it takes the constant polynomial. Yeah, so it's an injective function. The next thing one has to check is that it's a ring homomorphism, and that will tell you that it's an injective ring homomorphism. Yeah, so I of A plus B is F sub A plus B. Yeah, by definition of I, and what is F sub A plus B? It takes 0 to A plus B and it sends n and any other integer positive and all a positive integer to 0. Yeah, so we have to check that this is same as F sub A plus F sub B. Yeah, so but so F so let's just F sub A plus B evaluated at n is same as is 0 if n is greater than 0, and A plus B if n is equal to 0, but this is same as F sub A. Okay, maybe I'm trying to write things in a more complicated way, but this is same as F of F sub A of n plus F sub B of n. Yeah, and this is same as F sub A of 0 and plus F sub B of 0. Yeah, so that tells you that F sub A plus B of n is equal to F sub A of n plus F sub B of n for all n in Z plus Z greater or equal 0. Yeah, so that tells you that F A plus B is equal to F A plus FB as two functions, sum of two functions. Yeah, this is the addition in the polynomial ring. Yeah, so now I'm getting rid of this funny addition. Yeah, so technically I should put a circle here, but let's not worry about it. Yeah, so that tells you that this behaves well with addition. And then the second thing to check is that it behaves well with respect to multiplication. So I of AB is F sub AB. Well, what is F sub AB? So we know what F sub AB is. Let's just try to compute the other side, yeah? And what is I of A times I of B? This is F sub A times F sub B. Yeah, so I should put a circle again here, but let's not worry about it. So actually let's just put circles since we are doing it for the first time. Yeah, so so we want to show that these two functions are same. Yeah, so so let's just evaluate these two functions. So F of A dot F sub A, F sub B evaluated at n is, you know what it is, it's sum I equals 0 to n f sub a of I times f sub b of n minus I. Yeah, but this is so when so this is going to be, so if n is positive, then one of them has to be positive. Yeah, and so it will be 0. Each term will be 0. So this is 0 if n is greater than 0, and if n is equal to 0, yeah, then of course I must be 0 and n minus I must be 0, and what you get is AB, yeah, which is precisely equal to f sub AB. Okay, so this shows that this is indeed so hence I is a homomorphism, ring homomorphism. Okay. Okay, so maybe we'll stop here. So if now is the time to ask questions. Okay. Okay, so you have some questions?
Sir?
In the in this portion, instead of using the functions notation because it's complicated, can we use the sequence notation instead? Because that will make the proofs neater.
We'll use the polynomial expression, of course, later on. This was just to...
So not the expression, I mean the infinite tuple notation. That will, I think, make the proof neater than it's now.
Instead of writing function notation, you want to do subscript notation.
I mean, because in analysis we defined a sequence as a function from n to r, and so we can do something like that here also. So
so
using
we
the
are saying that
infinite
instead
tuple
of writing a of n, we can write it as a sub n. Yeah, instead of this, you want to write this. Yeah, you want to replace this. Is that what you are trying to say?
Yeah, not just that. I mean, suppose we are trying to prove some equality condition like a equal to b or something like that. So instead of evaluating at each n, if we write all of them in one tuple, then we can do it at one go instead of writing at each n. So
yeah, sure. So I mean, yeah, I don't think philosophically it makes any difference, but okay, it helps you think somewhat differently then, of course. But anyway, I mean, we will get rid of all this function notation from the next page, the next time onwards. We'll think of Rx as polynomials in this sense, yeah, in this sense. And this a bracket n will be replaced by a sub n and so on. Okay, so we'll think of polynomials in this sense soon. So from now onwards, more or less after this class. This is how one should think of polynomials, and we'll think of it that way. Any other question? You want to go to some other page? Okay. So I hope today I wasn't very fast. So if you have some, anyway, if you have some comments or questions on the notes, you can just post it on Google Classroom or and so. Okay.
Sir, in the definition of ideal rings, do we take that unity is there?
In the definition of ideal
ring.
In the yeah. So for definition of ideal, we want the ring should have unity. I don't think I've seen any place people considering ideals in rings which do not have unity. Okay, subring, it's okay. One can think of subrings as rings which may not have unity, but ideals, I mean, it will be useless if you don't. But anyway, I mean, most of the rings we will work with will have unity, yeah? Or all the rings which we will work with will have unity. Some of the subrings may not sometimes have unity, but it's okay. I mean, those are esoteric cases. You don't have to worry too much about them. Okay. But for us, when we consider ideal of a ring, we will assume it has unity. Any other question? So I was planning on doing something more on ideals, but maybe next tomorrow we will we'll talk about ideals more. Okay, so if there are no questions, then maybe we'll call it a day, and I'll put up the notes sometime today. Okay, and the video. Okay, okay. See you tomorrow. Bye.